Mars, a new frontier that humanity may one day set foot upon. This red planet shares many similarities with Earth, but also holds stark differences and unresolved mysteries. Today, we will delve into various aspects of Mars, including its day and atmosphere, the existence of water, its exploration history, and its future prospects. A day on Mars is almost as long as a day on Earth, lasting approximately 24 hours and 37 minutes. This slight difference is expected to make it easier for humans to adapt to the daily rhythm, if we ever establish settlements there. However, a Martian year is equivalent to 687 Earth days, or 668 sols in the Martian calendar. This discrepancy doubles the length of seasons compared to Earth, with a tilt of 25.2 degrees similar to Earth's 23.4 degrees. Mars experiences distinct seasons. Yet, the Martian seasons are far harsher than those on Earth. Even during summer, average temperatures remain below 20, while winter temperatures can plummet below -100. This extreme environment is influenced by the thin Martian atmosphere. Mars's atmosphere is only 0.6%, as dense as Earth's, and is composed of 95% carbon dioxide. Oxygen constitutes just 0.13%, a critically low level for human respiration. This thin atmosphere is due to Mars's low gravity, which is about 1/3 of Earth's. The weaker gravity makes it difficult for the planet to retain a thick atmosphere. Additionally, the thin atmosphere allows intense ultraviolet radiation to reach the surface, further complicating the possibility of life. The reason Mars appears red lies in its surface, which is covered with iron oxide, commonly known as rust. The planet's soil and rocks contain significant amounts of iron, which oxidized over time to form the characteristic red color. This phenomenon suggests that Mars once had water and oxygen. However, not all of Mars is red. Some areas feature black basaltic rocks or yellowish regions, highlighting the diversity of its surface. This reddish hue is not just a visual feature, but also a crucial clue to understanding the planet's evolution and environmental changes. Mars has two small moons, Phobos and Deimos. Phobos has a diameter of approximately 22 kilometers, while Deimos measures about 12 kilometers. Both are irregularly shaped, resembling asteroids more than traditional moons. These moons are believed to be captured asteroids, a theory known as the capture hypothesis. Another theory posits that they were formed from debris ejected by Mars. Phobos orbits just 6,000 kilometers above Mars's surface, making it the closest moon to its parent planet in the solar system. However, it is gradually spiraling closer to Mars, and is expected to either collide with the planet or break apart into a ring in the distant future. What about the presence of water on Mars? Currently, liquid water is almost non-existent on the planet. This is because the thin atmosphere does not provide sufficient pressure to keep water in a liquid state. It either evaporates or freezes. However, ice exists underground and in the polar regions. In 2018, liquid brine was detected 1.5 kilometers below the southern polar region. This salty water can remain liquid even at extremely low temperatures, offering a vital clue in the search for life on Mars. Additionally, traces of ancient rivers and lakes, such as those in Jezero crater, suggest that Mars once had abundant liquid water. NASA's Perseverance rover is currently investigating this area to search for signs of past life. Mars also has polar ice caps, known as the North and South Polar Caps. These are composed of water ice and dry ice, frozen carbon dioxide, and change dramatically with the seasons. During winter, carbon dioxide from the atmosphere freezes, enlarging the caps, while in summer, the frozen carbon dioxide sublimates back into the atmosphere. These polar caps are critical for understanding Mars's climate and atmospheric cycles, and are being studied as potential water resources for future exploration. One of Mars's most striking natural phenomena is its massive dust storms. These storms can cover the entire planet and last for weeks or even months. They are caused by the thin atmosphere and the sun's heating of the Martian surface, which creates pressure differences and strong winds that lift dust into the atmosphere. The storms can also self-amplify as the airborne dust blocks sunlight, cooling the surface and intensifying temperature differences. These storms have even affected Mars rovers, such as the 2018 storm that ended the mission of the Opportunity rover. Addressing these dust storms will be a crucial challenge for future exploration and colonization efforts. The history of Mars exploration is equally fascinating. In 1965, NASA's Mariner 4 spacecraft captured the first images of Mars. In 1976, the Viking program successfully landed on the Martian surface and provided detailed data. Since then, missions such as Sojourner in 1997 and rovers like Spirit, Opportunity, and Curiosity have revolutionized our understanding of Mars, discovering water traces and organic compounds. The latest rover, Perseverance, is collecting rock samples in Jezero crater to bring back to Earth. Additionally, the Ingenuity helicopter made history by achieving the first powered flight on Mars, showcasing the potential of innovative exploration technologies. Mars's topography is more grandiose and diverse than Earth's. One iconic feature is Olympus Mons, a volcano that stands 22 kilometers tall with a diameter of 600 kilometers, making it 2.5 times taller than Mount Everest. Another is the Valles Marineris Canyon system, which stretches 4,000 kilometers and plunges 7 kilometers deep. These formations provide critical insights into Mars's geological history, shaped by volcanic activity, water flow, and wind erosion. However, many details about their formation remain unknown. The challenges of colonizing Mars are numerous. Low gravity weakens muscles and bones over time, and the lack of a protective magnetic field exposes the surface to harmful radiation. Additionally, the Martian soil contains perchlorates, toxic substances that make it unsuitable for agriculture without treatment. Nevertheless, research facilities on Earth, simulating Martian conditions, have successfully grown crops, offering hope for sustainable living on Mars in the future. Moreover, bold plans to terraform Mars are being studied. These include melting the polar ice caps to thicken the atmosphere, releasing greenhouse gases to warm the planet, and generating artificial magnetic fields to shield Mars from solar winds. These ambitious projects may take centuries or millennia to complete, but are vital steps toward realizing the dream of Mars colonization. The future of Mars is boundless, driven by science and imagination. A century from now, thousands of people may inhabit Mars, in underground cities or domed habitats. Mars could also serve as a launchpad for deeper space exploration, such as missions to Jupiter and Saturn. The evolution of Martian civilization and its cultural impact are questions that our efforts and technology will answer. Mars reveals its grandeur through the remnants of its natural history, while expanding our vision of what is possible. Turning this red planet into humanity's second home depends on our ambition and relentless pursuit of knowledge.